For the non-homogeneous recurrence relations, we have to find the particular solution along with the general solution. Now in this case we say the final solution Fn is equal to general solution GS for general solution plus PS, that is the particular solution. Now this portion we discussed in the previous part, how to find the GS. For the GS we will follow the same theorems, but for the PS we will follow the different theorems that we are going to discuss. Then we add the both conditions and then evaluate or calculate the recurrence relations. Let us see the simplest formation of a recurrence relation in the non-homogeneous form. Fn minus 1 minus 6 times Fn minus 2 is equal to minus 30. F0 is equal to 0. This recurrence relation is different from the recurrence relations we discussed previous, that it contains a constant terms on the right hand side. Rather, it does not contain n. It does not contain any term which depend upon n. But the constant itself is a problem for this recurrence relation. See how we write the characteristic equation of homogeneous part. That is the homogeneous part. What is the homogeneous part? This one is the homogeneous part of the equation. Then we cannot transfer minus 30 to this side. Why? Let us see. Here it is order is 2. It will become r square minus r minus 6 is equal to 0. Because this term minus 30, it is a constant term and we cannot transfer on this side. If we transfer this on that side, it will become 24. But that is the wrong conception, because from where this 6 has come, the origin of this 6 is the original term of the recurrence relation, and this 30 exists from the very beginning. It is a constant, so we never mix this constant with this one. It seems to be a constant, but it is not generated by a constant term. It is generated by a term of the recurrence relation. Now first we solve the general portion for the homogeneous part. That's the same manner. It's r square minus 3r plus 2r minus 6 is equal to 0. r minus 3 plus 2 into r minus 3 is equal to 0. Then r minus 3, r plus 2 is equal to 0, and r is equal to 3 and minus 2. We say these are the characteristic roots of the characteristic equation of the homogeneous part of the given recurrence relation. Then what is the general solution? General solution we write that is equal to a1 into first root alpha 1 raised to the power n plus a2 into alpha 2 raised to the power n. That is general solution is equal to a1 into 3 raised to the power n plus a2 into minus 2 raised to the power n. Say it is a part number 2. It is same as we discussed in the previous topic. Both roots are different. So the general solution is a1 into first root raised to the power n plus a2 second root raised to the power n. Then here alpha 1 is first root and alpha 2 is the second root. No, what's about this term minus 30? This 30 has converted this homogeneous recurrence relation into the non-homogeneous. So it requires the special treatment. That is the particular solution. No, the particular solution to 1. let the particular solution to the 1. Consider again, I stress on the term, it is constant. It is constant. If it is constant, then we say particular solution is also a constant. Say it is Q. Say it is Q. Q is constant, same as A1 and A2. Here Q is constant. So for non-homogeneous part, what we do, first of all, we consider the particular solution. Here is the difference. For the different conditions, there are the difference theorems along with the previous bifurcations. Let the particular solution is equal to Q. Q is a constant. Remember, here there is no n anywhere. So what we do, always put this particular solution in number 1. Put in 1. And PS stands for the particular solution. Remember, PS is equal to Q and Q is the constant. It does not contain n. When we put here in this way, it is Q minus 6 times Q is equal to minus 30. Q for this, and minus 6 for this. Why there is no change? Because I again stress on this point that this is a constant in front of the constant and it does not contain any n. If the n comes, then how will it change? We will see in the next problem. Here we calculated Q is equal to 5 simply. It is the particular solution of the given recurrence relation. Then we say what is the final solution. Therefore, here is the final solution. Fn is equal to general solution plus particular solution. Fn is equal to, that is A1 into 3 raised to the power n plus A2 into minus 2 raised to the power n plus 5. Take it number 3. One thing more remember clearly, as in the previous topic, we used these initial conditions at this point, at the point of the general solution. But in the non-homogeneous section, we will use this condition only after the finding the general solution plus particular solution at this stage. If these are given, we can find the value of A1 and A2. Otherwise, it is the final solution for a non-homogeneous recurrence relation. Or if it is given, then we see how to solve it. Then F0 is equal to 0 implies 4. N is equal to 0. F of 0 is equal to Fn is equal to 0. For n is equal to 0, Fn is equal to 0. So we put this condition in number 3. Here 0 is equal to A1 into 3 raised to the power 0 plus A2 into minus 2 raised to the power 0 plus 5. Or 0 is equal to A1 plus A2 plus 5. Here we get the first equation, A1 plus A2 is equal to minus 5. Say it is number 4. It is the first initial condition. Let us consider another condition. Say it is equal to F of 1 is equal to 1. Go from 3. From 3 we get here F of n. F of n is equal to 1 is equal to A1 into 3 raised to the power n. N is again 1 plus A2 into minus 2 raised to the power n plus 5. Then minus 4 is equal to 3A1 minus 2A2. And say it is the equation number 5. And we can solve these both equations simultaneously by using the simple algebraical conditions. Say Here multiply it by 2, that is 2a1 plus 2a2 is equal to minus 10. 3a1 minus 2a2 is equal to minus 4, and subtract the both the conditions or add it will be better. That is this, that is 5. a1 is equal to minus 14 and a1 is equal to minus 14 upon 5. Then we can find the second condition from either this or this equation. From 4 we get a1, it is minus 14 by 5 plus a2 is equal to minus 5. Then a2 is equal to minus 5 plus 14 upon 5. That is minus 25 plus 14 divided by 5. Minus 11 upon 5. a2 is equal to minus 11 upon 5. Put both values in the final solution, that is number 3. Therefore, the final solution for the non-homogeneous recurrence relation becomes Fn. What is a1? It is minus 14 upon 5 into 3 raised to the power n plus a2 means minus 11 upon 5 into minus 2 raised to the power n plus 5, and it was a particular solution. This is the final solution for a non-homogeneous recurrence relation containing the constant term. No, it is not always that there is the requirement for the complete solution. Sometimes the requirement is only the particular solution. If it is the only particular solution, then we will find only the particular solution.